Hi class, let's do some linear algebra. We've been exploring the idea that a single vector space can have multiple bases. In this graph, I've illustrated 3 different bases for you. I've got the standard basis, E1, E2 in black. Then I've got V1, V2 in purple, and W1 and W2 in green. You can actually see visually that these pairs all form bases for R2. In each case, the vectors involved are not collinear. Therefore, we know that they're linearly independent. And so they form this 2-dimensional vector space, and therefore all of R2. They span all of R2. So what this means is that any vector in R2 can be expressed as a linear combination of the vectors in each of these bases. I've illustrated one such vector for you in red, 15.05 and 9.9, and you can see how it breaks down into a linear combination. Here I've got a linear combination of V1 and then V2. You can tell it's a linear combination of these things because they're parallel to the vectors. So we know that this is some alpha times V1, and over here we've got some beta times V2, where alpha and beta are some real numbers. Similarly, for W1 and W2, here we've got some scale of W1, so say it's A W1, and we've got some scaling of W2, so this is going to be B W2, where A and B are also real numbers. So we can see that we can break down our red vector in terms of all of these bases. What we don't know is how to find the coefficients, alpha, beta, and AB. That's what we're going to be doing today. We're going to be doing change of basis. All right, let's go. First, we want to talk about vocabulary and notation. Okay, so as usual, V is going to be our vector space. And I'll just recall something for you. So say we've got a V1 and a V2, and it's a basis for V. Technically, V2 comma V1 is the same basis. It's made up of the same vectors. We want to capture order as well as the vectors involved. So we will say that V1, V2 is an ordered basis for V to capture 2 pieces of information. We want to capture the vectors, and we want to capture the order they are in. The idea here being this, that 1, 0, 0, 1, and 0, 1, 1, 0 are different ordered bases. For R2, for example. Okay, with that, definition. Say A is a set of vectors, V1 through Vn, and is an ordered basis for V. So say we've got some vector in our vector space. We know that V is equal to C1 times V1 plus ... Cn Vn, where the Ci's are real numbers. We know that we can express this vector V as a linear combination of things in the basis. There is a unique vector, as in there's only one way to do this. So we have established a unique vector. Here's the notation for it, v in square brackets sub a. This is going to be the vector made up of the coefficients. As I said, since there's only one way to express v in terms of this basis, c1 through cn is going to be a unique vector. This unique vector has a name. It's called the coordinate vector. Of v with respect to the ordered basis A, and the CIs themselves are called coordinates. Let's do a brief example. Example. Say v is the vector 8,000, 2,000. And A is the basis made up of the vectors 2, 3, and negative 1, 1. V sub A, the coordinate vector of V with respect to A, is 2,000, negative 4,000. And the entries of the coordinate vector are called coordinates. Note, here's some new notation I'm going to give you. If A is the set of vectors 2, 3, negative 1, 1, the square bracket A is going to be the matrix where those vectors appear as the columns in the correct order. So the reason that I introduced this notation is so that we can say this. The vector V is going to be the matrix A times the coordinate vector of V with respect to A. In this particular example, we can check that 8,000, 2,000 is 2, negative 1, 3, 1 times 2,000, negative 4,000. All right, let's actually figure out how to find our coordinate vectors. First, we're going to have a setup. We need a few bases. Here's 1, 0, 0, 1. Standard basis. Here's another basis. 1, 1, 2, 1. Here's a third. Negative 3, 1, negative 1, 1. Here's an exercise for you. Check that A, B, and C form bases for R2. All right, let's check out this vector here. The vector 2, 1. Well, 2, 1 is going to be 2 times the first standard vector plus 1 times the second standard vector, so that V sub A, the coordinate vector with respect to the basis A, is 2, 1. But we know that since B and C are also bases, we can express this vector 2, 1 in terms of the other vectors. So it should be something times 1, 1 plus something times 2, 1. It should also be equal to something negative 3, 1 plus something negative 1, 1. We want to find out what these things are. We're looking for the coefficients. To do this, we need a transition matrix. Definition. The transition matrix corresponding to the change from ordered basis, say V1 through Vn, to ordered basis W1 through Wn, is a matrix S, such that Sx is equal to y, where x, of course, is some vector x1 through xn, and y is some vector y1 through yn. Sx is equal to y if and only if x1 v1 plus dot 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 xn vn is equal to y1 times w1 plus all the way up to yn times wn. S is the matrix that takes in the coordinate vector with respect to the first basis and spits out the coordinate vector with respect to the second basis. Let's find it. Finding coordinate vectors via the transition matrix. Here's what I want you to note. That the matrix made where the columns are the vectors in the basis A times the coordinate vector with respect to A is the vector in question. And it's also going to be equal to B times the coordinate vector with respect to B, which is also equal to C, this matrix, times the coordinate vector with respect to C. Because A, B, and C are made out of linearly independent vectors, the matrices that they create are going to be invertible. And that's the key idea. So A, V, A is equal to B. Let's take this little example. And so VB is going to be B inverse as a matrix times A times the coordinate vector with respect to A. This is going to be the transition matrix from A to B. It takes in the coordinate vector with respect to A, and it spits out the coordinate vector with respect to B. Let's just correct the notation here. There we go. Let's do a concrete example. In our VB, for our particular example, A is 1, 0, 0, 1, and B is 1, 1, 2, 1. So VB, the coordinate vector with respect to B, is going to be the inverse of the matrix B times the matrix A times the coordinate vector with respect to A. This is the transition matrix from A to B. This is equal to -1, 2, 1, -1, 2, 1, which is 0, 1. This 2, well, this guy right here, is also the transition matrix. What this means is the vector 2, 1 should be 0 times 1, 1 plus 1 times 2, 1. There's your example. Let's do another example. Example. The coordinate vector of V with respect to C should be the matrix made out of the C vectors, inverse, A, times the matrix made out of the V vectors, A vectors, times a coordinate vector of V with respect to A. Let's just do a little inverse work. This is A, and the coordinate vector with respect to A. What we're going to get is -1/2, 1/2, -1/2, 3/2, 2, 1, This is the transition matrix from A to C. And it is equal to, well, this product is equal to -3/2, 5/2. So 2, 1 should be equal to -3/2 times -3, 1 plus 5/2 times -1, 1. Here's an exercise for you. Find the transition matrix from B to C. You might have some lingering questions. So one of the ones that I want to point you to is there a way to find transition matrices directly from the ordered bases? Instead of, say, involving a specific coordinate vector? The answer is yes. Think on this. Talk to you next time.